It jumps.
Alright, so are there any specific questions before I get into finishing off 14.2, getting into 14.3? Okay, alright. I do want to do, let's see, there's a page 987, number 64 in your homework. Kind of focus you guys on that. Remember the two types of integrals that we can do over vector fields? Possibly. They both are like this, f dot something. F dot something.
Line integrals.
Well, that would be the first thing is a line integral of a scalar over scalar. Alright. Then we have these integral over vector field.
Yeah, tangent and orthogonal.
Line integrals over a vector field. There are two main types. Because as you go, if you're in a vector field, as you go around something like this, you can either collect, you can add up all of the parts of the vector field that agree with the direction you're going, or you can add up all the parts of the vector field that are orthogonal to the direction you're going. Now the reason you might want to do this is because, for example, you want to know, you got this thing that's blowing air in all these different directions. So at some point you want to know how much total volume of air particles are going through that surface there due to this blower, right? You might want to know something like that. Or you want to know how much energy is being set off by this light source in the middle. You want to know how much energy actually going through some imaginary surface here as you go further and further away from it. You kind of with me? That would be the type that's orthogonal, because I wanted to go through the surface. I wanted to be orthogonal to the surface. Whereas this one would be just, as I move, how much of the vector field do I collect that agrees with how I'm moving? This would be the tangential piece. So that's going to be the one that starts off like this. This is the one that we talked about at the very end of class last time. That would be like this. That would be the one that's orthogonal, because I want to get the part that's in the direction of the normal vector. Normal vectors, of course, will be orthogonal to the tangential piece. All right, how are we doing so far? And really what we're getting down to, any point, the whole idea of a vector field is at a point what's true at that point, given some vector field definition. At any point what exists there due to this vector field. A vector, there you go, so that makes sense. And that vector has components lying along whatever the hell coordinate system I want to set up. You with me? So, I mean, if I have a vector sitting here, and I have this coordinate system, it has a piece like this, and it's got a piece like that. Right? Or I could have turned this thing. You kind of with me? Mm-hmm. All right, so what we're talking about here is what's setting up my coordinate system at every point. And I really want you to realize this is the concept. This has nothing to do with the nuts and bolts, but this is what the hell you're doing when you do the nuts and bolts. At every single point, we have a different coordinate system. At this point, I have that and I have that. So part of the vector field is lying in that direction, and the other part's lying in that direction. Or maybe it's all in that direction. Depends on the vector field. Are you guys kind of with me? A little bit? So if I have a vector field, very simple vector field like that. No, Jeff. And I come in here with this. As I'm moving like here, this would have 0 for this one. Right? Because what's happening right there? The vector field is perpendicular to it, roughly. Just go with me. So that would be 0. This would be maximum there. Whereas right here, it would be the reverse, because now it's totally tangential. So I have two main options. You can add up all the pieces that are agreeing with how you're going, or you can add up all the pieces that are orthogonal to the way that you're going. The funny thing is, this is the one we see most often. This is the one that makes the immediate most physical sense, actually. But this is the one that actually we use more often. That's why I didn't really assign too many of these in the homework. Okay, how are we doing so far? Is that roughly all right? So that's why there's two main ways to do this, because our functions are vector-valued functions. And vectors have components. So there should be two main ways to do it because vectors in 2 space have two main components. Whereas scalars, well, they're freaking scalars. One way to do that. Okay. So this problem, number 64, just to kind of cut to the chase a little bit. Blah, 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 blah. Oh. So I'm going to let you guys do A and B, but part C, you should end up with this. Now what is this? What kind of a vector field would you say this is? Think about that for a minute. What kind of a vector field would this be? Is it position dependent? No, wherever the hell I am. It's this. It's this vector exists at every point. It's just that. I don't care where you are, that's what it is. You with me? And that kind of makes sense. There's a lot of situations where, especially defined in a little narrow area, the wind is all going that way or something. It's always the same no matter where you look. It's always the same. Okay. So on part D it says this. Find the heat flux across the boundary where'd it go? So we have this vector field, and roughly that would look at any point it's pointing 50, 25. So they look roughly like this, just to kind of not worry too much about scale, but to at least get the direction sort of right. You guys with me? 50, 25, 50, 25. Every single point, it's pointing in that direction. So nothing major here. So this problem is all about heat flow. So obviously this heat is flowing at a constant rate, not really a rate, but in a constant way everywhere. So this, x equals 1, is here, and then 0 to 1 on the y, so that just defines this line. So this is exactly the idea we're talking about for flux. I just want to know how much heat is passing through that line. That's the flux. Okay, what are we doing so far? Okay, so here's what we got to do. And what do you think we have to do to get going on this problem? What's sort of like the first step on either one of these types of intervals? What's the first step?
Find our limit.
Find
The limit?
Not really. In the process of doing something, we have to find the limit. And this guy, I think last time we figured this out. I can't remember what form we put it into last time. Yeah. If f is this integral becomes f x prime minus g y prime.
Oh, you had fy prime ft minus g x
They have it
prime.
reversed? Yeah. Is it supposed to be? Yeah, it is supposed to be.
Y prime of
Thanks,
t.
thanks. That makes more sense. Cool. Let me just stop right there. That's where we got you last time. We were talking about this flux. The second way to look at line integrals and vector fields is the part that's orthogonal, and this is what we came up with. And what part of this kind of makes sense? Orthogonal to xy would be y negative x. So it kind of, that's as I was writing, I knew something was wrong, but that makes sense to us now. That I can kind of see the orthogonality built into the integral itself. Now last time we went through the process of showing why it is this, but looking at the end result, that kind of makes sense. It is kind of set up orthogonally. How are we doing so far? Not good, okay. All right. These things happen. So to do this then, I need to first figure out what r of t is. So then I can actually figure out what the y prime piece, the x prime piece, I got the f and the g pieces up here. How am I going to define this line segment here? How do I define that line segment? to define that? Well, this part of it's really damn easy.
X equals 1.
X has got to be 1. That's everywhere, every single point, X is 1.
Y equals absolute value of Y.
Just Y.
T, right? Where T goes from 0 to 1, yeah, sweet. So that's R of T, 1 comma T. Is that cool? I mean, that's this line segment right there. At 0, it starts off at 1, 0, and then goes to 1, 1. Kick-ass. And it picks up all the points in between as T varies from 0 to 1. Is that how we know so far? Okay. So the first step on both of these is to find that R of T. That, how do you write the curve parametrically? How do you write that in this form? Okay. So think, oh, there it is. So what's R prime? 0, 1. This is also known as X prime. Is that cool? That's X prime. Dx dt if you want. And this is Y prime. Dy dt if you want. And what's F? What's the F piece of the vector field that we're working with? 50. This is almost too easy, but it's the only one I gave you. And I'm even going over it with you, which should tell you something. I'm probably not going to have many, if any, of these on the test.
Yay.
Yay! Some of you should go boo, because this is actually not that bad. But how do I set this up? The F component of the force, of the field, that's 50, times Y prime, and what's Y prime? 1. Minus the G piece,
25.
times X prime, which is 0. And T goes from 0 to 1. What I really desperately want you to get, I know this is still semi-new to us, but that first step of setting up R of T, it still defines the pieces that are in here, doesn't it? I mean, this piece is in terms of, well, it's in terms of this. That's why this is almost too easy, because these are constants. But I still have to rewrite them in terms of X and Y according to this. If I had any X and Y's up here. This is all got to be a function of T inside. Yeah?
That's what I'm curious about. The equation that you wrote last week was Fy prime of T minus G.
Yeah, I'm just leaving out the of T. I do that a lot, sorry. Yeah, because once you set up R of T, X and Y are functions of T. And when I say that, I mean, this is the X and Y component of that R of T vector. Yeah.
So what we did is we got the component of the vector that is vertical or orthogonal to the line that we have, and then we integrate it over the interval from 0 to T.
Basically, we defined a normal vector here. In the process of doing this, there's basically the normal vector. It's got to be orthogonal to X prime, Y prime, right?
Yeah.
And the easiest way to do that, I think, well, we were talking about this earlier, but this actually works beautifully here, is to do this. Those are orthogonal then, aren't they? That's why that's what shows up. I want to dot this, dot it with the orthogonal piece to this, which is this. And what's dot product? F times Y prime, G times negative X prime, there you go. Yeah?
What I'm wondering is if you have a negative Y and positive X, you get a negative for that interval. So even though it shouldn't change anything, it does, right?
Well, if you go, so if you have negative Y, positive X, I don't know if you remember.
For the orthogonal.
I'm with you.
Yeah.
But we talked about that when we did the derivation. We had to make a choice somewhere, and we chose to use the positive z-axis as our, the k vector to kind of use as a intermediate to do a cross product. What do you need to be able to do a cross product? What kind of vector can do a cross product? It's got to be 3-component vector, right? It's got to live in R3. So we chose the k, and if I chose the negative k, that would have kind of turned this whole thing around. It would have still worked, but everything would have been kind of reversed. Yeah. All right. Yeah.
The vector that you circled at the top, where'd you get that from?
Oh, this is R prime, right? How do we get R prime? We just take X and Y and take the derivative.
Right.
So what's a vector that's orthogonal to it? Turn it around, make one of them negative. And I'm pretty sure I pointed this out when we did the derivation. I did say that in general, it doesn't matter where that negative is. But because of the way we design this thing, it's got to be this way. And that's why it shows up like that here. It's just a dot product between these and this. Cool. You can see that orthogonality in there. Okay. All right. I'm hopeful. So the concepts here are really not out of reach. They're right there. And if you don't read your math book, I don't understand you. And you probably don't understand me either. You've got to read through your math book and make sure, can I tell what the hell they did from this step to this step? And if you can't, it should bug you. You should go, shit, what the hell did they do? And then you come ask me and I say, oh, that's a typo. No, I don't. And say, no, this is what they did. You should try desperately to figure out, can you read that book and understand what they're saying? If you aren't even trying that, that might explain if you have a very low grade. Yeah?
So where did you get the zeros and ones?
Oh, when we define this.
Yeah, for the t, right?
Yeah. So, yeah, there you go. So this is one case where if they would have said 0 to 2 here, this is one case where the t would have gone to 2. Remember what I said if we do line segments, and if we do it, the initial position point plus t times the direction vector. You with me? Didn't it, like the y equals mx plus b? If we do it that way, t will almost always go from 0 to 1. We really didn't do it that way here. We did it a lot easier way because of the fact that this was just so easily defined. It goes from 1, 0 to 1, 1. That's why t's got to be between 0 and 1. If it would have went up to 2, I would have probably just said t 0 to 2. In this case, are you guys with me? Okay, cool. Because we really didn't do it like initial position plus t times a direction vector, did we? We didn't do that. We just did it much simpler because it's such an easy little thing to do. Okay, maybe. I mean, if I wanted to, what point does it start at? 1, 0. What point does it end at?
1, 1.
So then what's the difference between those two?
1.
1, 0, 1. Yeah, thank you. I'll get it someday. So then the line would have been, you start at 1, 0, and you add t times 0, 1. And what do you get when you add those together? 1 plus 0, 0 plus t. You get 1t, of course. How we doing? Yes.
When last week when we found out how you defined the normal vector as the thing that you just erased.
Oh, certainly.
You had it divided by magnitude r prime of t. Does that come into play here?
That's because of the fact that t, so let me see what you're looking at. T is r prime over the magnitude of r prime. Where are these guys go? There he is. So we got, t is the tangent vector, and it's got to be a unit vector. It's actually tangential unit vector. It's got to be r prime divided by the magnitude of r prime.
I just answered my question.
Cool.
Okay,
And that's really nice because remember, ds is r prime,
Yeah, that's dt.
and those will cancel out when you throw them all together. Yeah. Okay. Okay. All right. We all love this stuff so much. So, I mean, this is the part that I know is kind of frustrating. It's the fact that the math itself is really not that difficult. It's just that I can understand if you're not reading the book and you're just getting what you can from me, that you might not have a full grasp of what's going on here. You desperately, I'm one resource and the book is another major resource. So if you're not reading through it and really making sure you understand what the hell they're saying, you're missing out. Okay. What I do though, just to let you know, is I actually do give you the forms. You know what I mean? Like the forms of the integrals. Mm-hmm. So I give you the form for each vector, like we just had up here. And I give you the form for the tangential, the normal, and they give you a form for line intervals, scalar intervals. Right, so I'm going to give those to you on the test. You just have to put the right things in the right place and do the integration correctly. Yeah?
I was just going over my notes. I think you just asked the same question. Normal vector is the tangent vector crossed with k.
I love it.
What's k?
K is the z, right? I, J, K. I, x axis, y, j axis. The other way around. K is the z axis. Cool. So let's do this. Do you guys still have the stuff we gave out last time, the 14.1, 14.2? Quick quiz. On the back was the 14.2. We did the 14.1. I don't think we did the 14.2 yet. So if anybody needs a copy. So I'll tell you what, in the interest of time, I want you guys to work on that at home, and I'll have the answers for you on review day this Wednesday. We have desperately got to get this last section that we covered.
Wednesday's review.
Yeah. Wednesday's review for the next test. Okay. Yeah, it's almost 2 o'clock. Yeah. So let's see. So here's what we're going to talk about. In Math 180, remember those days? Good old days? Didn't know how good you had it, right? In Math 180, if I wanted to integrate some function between a and b, and let's say f is the antiderivative of, remember those good old days? Anybody know what I'm trying to set up here? What would that be then?
The area.
No, don't describe it to me geometrically. Tell me what the answer would be in symbols. In fact, you guys know exactly how to do this. What's the integral of x, 2x dx from 0 to 1? Square divided from 0 to 1, so you put a 1 in, minus you put a 0 in. So the antiderivative you found was x squared, and you put 1 into it minus putting 0 into it. I don't know if you guys remember that. So the big F is basically the area below that. So if you go up to 1 and then go up to 0 and subtract them, you should get the area between the two. That was the basic idea. And the reason it was so damn easy is the reason that so many things in this class are a lot harder. How many derivatives can you do here? 1. Really, right? You just do df dx. Right? You guys, there's really only one way. You could argue you can go that way, but that's kind of silly. We just go that way. That's it. But now we know in this class, in multivariable calculus, you can do at least 2, if not more, however many. Let's say in r cubed, you can do 2, fx, fy. Right? You guys still with me? And then we have these directional derivatives. Shit, depends on which way you're facing. Here, one derivative. You're looking that way. Why? Because you got to. That's the only way you can look. The minute I give you more dimensions in your domain, oh shit, I can look in all these different freaking directions. And the derivative is different as I look in every direction, right? Possibly. So, but there is a way to capture it. If I have a specific type of function, I can do exactly this with it. That's the purpose of this section, is to talk about how to check when you have that kind of function, and then what can you do with it? What else does it mean? That kind of thing. But the most immediate thing to me would be, shit, I can do this. I don't have to do any parametric crap. Do you guys realize what's going on? I want to get to the point, and let me just show you what it's going to look like eventually. If I'm integrating some vector field Let's see. Which way do I want to do it? Let's just leave it like that before I get too deep into this. I want it to end up being, let's say it's from point A to point B. That's why they're capital now, right? I want to be able to get to where it's going to be some function. Let me kind of do the reverse. Let me make sure. I'm hoping you guys don't freak out. It'll be some function evaluated at B minus some function evaluated at A. I kind of had to make it small f because I already used big F here. But basically the same idea, just evaluated at points now instead of at single inputs. You know, x, y points. How we doing? I want to get here. Because then if I have that kind of function, screw everything we just did in 14.2. I don't need to parametricize anything. I just plug the point into the function, minus the other point in the function, and I'm done. Right? But it has to be obviously a very special function that works really nice. It does exactly what it has to do. In general, I can't do that. That's why section 14.2 exists. Okay. So, now, if I just come up with a function like xy comma y minus x, I can almost guarantee that that will not work like this. One thing you got to realize, why do functions in Math 180 work so well? What can you do for almost every function that makes this so easy to do in Math 180? You can find what? You can find f. You can find a function whose what is this? It's beautiful. So think about that. What would that mean has to happen here? I need a function whose derivative, and what in that case, what do I replace that word with now? Gradient. I love it. Whose gradient is this? That's the idea. Here I'm guaranteed, except for some functions that, you know, like are not elementary functions, like e to the x squared, that kind of thing. Are you with me? But most functions I can certainly find an antiderivative for, something whose derivative is this. Here, I've got too many degrees of freedom. They both have to kind of come from a single source. So what do we normally use for that symbol that kind of talks about what I'm talking about? What do we normally take the gradient of? I like it. So what we're trying to do is find this. Who remembers what that's called? Potential function. I love it. And if you're in physics, that should sound vaguely familiar. They have a negative out there, but it's basically the same idea. Okay. If you're not in physics, forget what I just said. All right, so part of this is, how do I tell if a function that I have would have a phi that exists? And if I can tell it does, how do I then find it? And we call that, if it does, if some given vector field has a phi such that f equals del phi, derivative gradient phi, then we call f a conservative vector field. That also is related to some physics ideas. Okay. So one immediate visual idea we can get from this, before we even get into how do we find out and how do we find it, is here's what the visual of this is. If I have some vector field, and I don't care what it looks like, let's just say it looks like that has some vector field, and I have a point here and a point there, so I'll make it straight across. And I want to know, okay, I want to have the line integral from A to B in this vector field. If it's conservative, doesn't matter what path I take. Because if it's conservative, I'm guaranteed that it will work, shoot, I erased it. It'll work like this did, right? I didn't really erase that. I'm guaranteed it'll work like that. And so the integral will only depend on what? The endpoints. So I don't care if I do that path, if I do this path, if I do this path, if I do this path. I don't like you. No, maybe I do. No, it doesn't matter what path you take. If it's a conservative vector field, I don't care. So it's path independent. There's another name for this. Because it only depends on the endpoints, on the limits. So obviously these are really freaking cool functions to have to work with. It's very easy to work with. Okay, so that's enough of the ideas and the visuals and everything. Let's see the math. Let's see how the hell do you tell if you have it. So let me ask you this. If there is a phi for some given vector field. So I have a given vector field. Let me call this, yeah, that's fine. If phi does exist, where f is the gradient of phi, that's ours. Then what does little f have to be?
The x component?
Second?
Partial x?
Yeah, phi partial x. And what does g have to be?
Partial y?
Phi partial y. So the interesting test, the test is kind of cool, and I think a few of you guys have had GPQ, and this is going to sound very familiar to a form of an easily differentiable equation. Exact equation, I think it was. Oh, it's been a while since I taught it, but I think it's called exact. If I take fy, what will that be in symbols here? That'll be phi xy. If I take gx, what will that be in symbols here? Phi yx. What are we doing so far? So then if my function is such that it's a function whose second derivatives match, and that's most of the functions we know, have this property. What must be true about fy and gx? They must be equal. Now, if this whole argument was if phi does exist, then this must be true. But it works both ways, thank God. It's an if and only if you understand the difference. If and only if means it goes both ways. So if I can show that fy equals gx, then there must be a phi that exists. So check out this one I wrote up here. What's fy? Well, what's f? Let me start there. Just make sure everybody can understand what the hell I'm talking about. What's little f?
xy.
That's little f and there's little g. What's fy?
X.
Cool. And what's gx? -1. So could there possibly be a potential function for this? No, this vector field did not come from the gradient of some other function. You with me? So this guy will always be difficult to integrate over. Right? More difficult than it would be if it was conservative. How are you guys doing so far? Alright, so here's a good one that actually works. I like this one. And then we'll use this one to talk about how to find. I'll tell you what, we throw this general thing. What if, before we do this example, because it's in 3 dimensions, let me see if you guys understand this. And this one, I don't think I'll make you memorize this either, but I'll show you how easy it is to memorize. When there's 3 components, it's nowhere near as easy as this. This was easy. That's the y piece, take it with respect to x. That's the x piece, take it with respect to y. This one, not as immediately understood what's going to work here. But remember, what is this again? If phi does exist? If phi does exist, that's phi x, and that's phi y, and that's phi z. Is that cool? You guys with me? Does that take the gradient of phi plus? So if I do fy, what does that have to equal to?
Phi xy.
No, I mean, what other piece of this partial does it have to equal to? Like here, fy equals gx.
H.
Thankfully here, what would that be? Wouldn't that be phi xy? You want that to equal phi yx. And what would that be? How would I get phi yx? Gx. Alright, so that we recaptured this, didn't we? So if I do fz, bless you. Let's see if I can escape this business and say, what does that have to equal to? So fz has got x and z in it. So it's got to equal to hx, because that would have z and x in it. You guys see how to mix and match these?
Yes.
Maybe not. What would, what's the only thing we know about? What would GY have to equal to?
Wait.
Not GY, I'm sorry. GZ is the one we left out.
HY.
Yeah, GZ would have to equal to HY, because then they would have the Y and the Z pieces together. Okay. Those are the three things you have to check to see if it is a conservative vector field, something that has a potential function. So, look at this guy here. Let me see if you guys. Oh, go ahead.
Sorry, I missed what's in the what's in the dots.
Basically the same idea. Like here, this would be phi xz. This would be phi zx. That's why these have to equal, because that would be what I have to check to make sure that the mixed partials are equal to each other. Is that cool? All right.
Okay.
So the check is pretty easy. It does sound familiar from DiffQ, right?
Oh yeah.
Oh yeah. So in case you have to take DiffQ, you've got a little head start. So what about this guy here? Check to see if that's conservative, if it has a potential function. If it was 2 dimensions, all you have to do is check that, because that's the only possible cross differentiation you can do. 3, I've got that many to check.
What was the?
Yeah, this, you gotta love this. This is pretty quick, but I'll make sure we're all on the same page.
What was it? Phi for g of x in the dots?
Oh, GZ?
Yeah.
So G is phi y, so this would have been phi y z, right?
Okay.
Because it's z on top of y. H was phi z, this would have been then phi z y. So the mixed have to equal each other.
Got it.
So there's several different ways to kind of memorize that. Yes, sir?
Why does Fy have to equal Gx?
Because we know that these mixed partials have to be equal to each other.
How do we know that?
That's something we've known for a long time, hopefully.
Okay.
Right, and that's kind of related to, remember D? Why do I only need one thing there? Because Fyx is equal to Fxy for well-behaved functions, which are really the only ones we're looking at, to tell you honestly. This course could be a lot more difficult. But we're only looking at well-behaved functions. Believe it or not. So what do you guys get for all these partials?
1.
Fy is 1, right? And that's equal to
1.
Gx. Oops, Gx is 1. And so forth. Everything's 1. You with me? All right, so like Fz is 1, and Hx is 1, so forth. So all of those mixed partial derivatives are equal to each other. What that tells you is they all must have come from some original function, some phi. Some original function. If you didn't have an original function, if each of the pieces of this were just like thrown up there with no thought, then the mixed partials don't have to equal each other. They didn't come from a single function. So who cares if you take a second, another derivative with x and another one with y? Why would they have to equal each other? If they do equal each other, these must have all come from the same function. And in fact, more specifically, it would be the gradient of that function, whatever it started off as. I love that idea. 2 reasons. It's really cool and it's really easy. I'm hoping. And this is brand new to a lot of you guys, so you just gotta let it sink in. But how the hell would I go about finding what phi is?
Integrate.
Finding phi. It's a really strange movie. Yeah, I'm going to do some integration, obviously, right? So this is little f, but what is it more specifically in terms of phi? What is this piece?
Phi partial x.
Phi x. Now stay with me. We're going to do this with a specific example because I think it's a lot easier to explain it with a specific example. Very good idea. How do I get phi? I just integrate with respect to x, right? Because it's been differentiated with respect to x. So what are y and z then according to the interval I'm about to do?
Constant.
They're constants. So then this tells me that phi must be
Parameters.
xy plus xz plus, uh-oh. Now here's where we get a little freaky. I can't remember now if we've done this before or not. When you integrate with respect to x, this will of course be a constant. But what are constants according to the integral?
Y and Z.
Any function of y and z. So instead of putting plus c here, you put plus c, oops, function of y and z. Oh yeah. Let me say that again. We integrated with respect to x, like undid a partial differentiation with respect to x, therefore y and z are constants. So when you do your plus c like you have to do in Math 180, and I even forgot to do that when I was a student, but when you do that piece, it's actually a function of y and z. I'll see if you guys, again, I'm a major geek, so I have no point of reference for you guys, but personally I just kind of love this way of doing things. I know what phi is to a function of y and z. So what else do I know about phi to begin with? What's that?
That's phi sub 1.
Phi y, right? Phi x, phi y, phi z. So if I take phi y with what I know phi to be now, what's phi y according to this?
X, Y plus.
Careful. X plus, this goes away. Right, phi y, so the x is still going to be there. Derivative with respect to y. This has no y's in it, it's a constant, it goes away. Plus,
C prime.
and I only put a little c, y, y, z, just to really tell myself what the hell I just did. So think of that like putting a c prime there, but I want to be a little more specific for myself. Are you doing so far? I don't know if you guys went this far with the cube. Yeah, okay. And so that's phi y. I desperately want you to get this. Does it make sense that phi there? All I freaking did, I know what phi x is, so of course I can find phi, right? At least out to this far. So if I take phi y from this, I get this, but what do I know phi y is? It's just fun to say phi y. What is phi y? It's this. So I know phi y from the phi I've found so far. Onomatopoeia, is that one? Yes. I know phi y from the phi that I've found so far. I can do that right here. And I know phi y from the original thing they gave me. So therefore, what is cy?
Equals
Equals z. And if I take a little integral there, what do I get?
Z Y.
Integral with respect to what in this case?
Y.
Y. See, that's why I put that right there, didn't I? So the integral with respect to y, you're going to love this. I know it, especially because we're running out of time. When you integrate with respect to y, this of course is going to be,
Constant.
yep, let me get it up here.
Y, Z. Whichever you want to put first.
Z, Y.
So you guys in the way back are like, what the hell is right? So when I integrate, I got yz plus a function of,
XZ.
no, careful. This is only a function of y and z. So what's a constant according to the integration with respect to y?
Function.
Z, a function of z. The same reason I needed this here is the reason I need that there. You can imagine that this whole process is the same, just a lot quicker and easier in 2 dimensions. Right? It's a lot more straightforward in 2 dimensions. That's why I figured, what the hell? Let's learn how to drive a manual first and do the harder one. Right? Automatic's easy after that. So then how do you think I find out what ZZ is?
Same thing.
So now what do I know about phi? I know phi is xy plus xz plus
YZ plus D.
yz plus dz. And the last thing I haven't used yet, if I do phi z, what do I get?
X, Y.
Nothing.
0, X,
X,
Y,
y
and
plus dzz. And what is phi z supposed to be?
X plus Y.
X plus y, right?
Same
Because
thing.
again, there's phi x,
So D-
phi y,
so
phi z.
0.
So phi z is supposed to be x plus y. So dz is
0.
0. So d of z is some true constant. Be careful, when you integrate 0, you get a constant, right? And we normally just go ahead and set that equal to 0. Diff Q, you don't. You talk about families and stuff. We normally just set that equal to 0. Just to make it a little bit easier to look at. So what at the end is my phi? What's my potential function? xy plus xz plus yz, and we just figured out that d is essentially 0. It's some constant. We just kind of picked it to be 0. Boom. So I don't know how much you picked up from that process. I personally love this process. It's just so neat. You can just sink your teeth into this process. You can just do it. You can attack it. That's got to be there. Figure out what the hell that piece is. That's got to be there. Figure out what the hell that piece is. So just you can see where everything's coming from. First time you've seen it, so maybe not yet, but well. All right, I think. Oh, very last thing. Let me ask you this: since we have this problem up here, how would you integrate? Let's see if they have a problem like this. Yep. Given this as f, how would you integrate this? And to be more specific, this works with the tangential. I told you this is the one that we see more often. To integrate this, I can then use, I know it's conservative, I know that the antiderivative of f, yes, the antiderivative of f is phi. And this is sorry, I left off what it's going to be from 2. Let's say that c is from 1, 2 to 2, 4.
Plug in the points.
Plug in the points. It's path independent. I don't care what path I take. It's not the line segment. It's just going to say any path from 1, 2 to 2, 4. So now it's going to be phi at 1, 2, oops, sorry, backwards check. Phi at 2, 4 minus phi at 1, 2. Just like it was in Math 180 when you integrated something, you just evaluated at the top limit minus the bottom limit. Yeah.
Is that in 2D?
Oh, I'm sorry, 3D. Thank you. Let's make 1, 2, 1 and 2, 4, 1. What the hell? So now all you have to do now is plug that into phi, minus plug that into phi, you're done. Because of the fact that it's a beautiful function, works beautifully, Math 180 ideas now work with it. Because you can't just integrate this we found out now is this. So effectively this and this cancel. The integral and the derivative cancel directly. Yeah, sorry.
Since it's path independent, it doesn't matter whether you do a tangential or orthogonal?
Now be careful. That would change entirely.
Oh, okay.
Because fundamentally. But this integral, I don't care what path I took. So one thing you could do is take any path you want, the straight line, and parametricize that and do that. You can actually do the whole thing that way. But since it's path independent, it's path independent because it only depends on the outputs at the two extremes. So just bam, I just do that. But that means that if I did it a different way, it'd come out the same answer every time. Cool.
Just like work.
What's up?
Just like work.
Oh yeah, exactly. Exactly.